Everything you think you know about tomorrow might have an expiration date. What if I told you that the sun, the very star that warms your morning coffee, powers your solar panels, and guided Apollo astronauts home, is quietly, inevitably, counting down to its own destruction? And when it goes, it's taking everything with it. Scientists aren't just guessing here. They've mapped out not one, not two, but 10 possible ways our entire solar system could meet its end. And some of them will genuinely keep you up at night. Hey, welcome in. I'm so glad you're here. This is Astromat, the channel where we take the biggest, wildest questions in space and physics and break them down in a way that actually makes sense. Today we're diving into 10 theories about how our solar system will eventually end, from slow stellar death to cosmic collisions you never saw coming. And trust me, you want to stick around until the very last one, because the final theory on this list is the most mind-bending of them all. If you love this kind of curiosity-driven space content, go ahead and hit that subscribe button right now, because we do this every single week and you do not want to miss what's coming next. All right, let's start at the beginning of the end. Think about the last campfire you ever sat around. You watched it burn bright, throw off heat and light, crackle with energy, and then, slowly, inevitably, it dimmed. The logs ran out of fuel. The fire died. Now imagine that campfire is 865,000 miles wide and has been burning for 4.5 billion years. That is our sun, and just like that campfire, it has a fuel limit. Here is what the science actually tells us. Our sun is a giant nuclear fusion reactor. Every single second, it fuses around 600 million tons of hydrogen into helium deep in its core, releasing an almost unimaginable amount of energy. That energy is what lights up every single morning across America, from the beaches of California to the coastline of Maine. But hydrogen is not infinite. NASA scientists and astrophysicists at institutions like the Harvard-Smithsonian Center for Astrophysics have modeled the sun's life cycle with extraordinary precision. The conclusion is clear. In approximately 5 billion years, the sun will exhaust the hydrogen fuel in its core. And when that happens, something dramatic begins. Without the outward pressure of nuclear fusion pushing against it, the sun's core will start to contract under its own gravity. As it compresses, it heats up. That extra heat causes the outer layers of the sun to expand, slowly at first, then dramatically. Our sun will swell into what astronomers call a red giant, growing so large it could extend beyond the orbit of Earth itself. Mercury gone, Venus gone, Earth likely consumed or scorched beyond anything recognizable. The same star that made life on this planet possible will be the thing that ends it. NASA's Kepler and TESS missions have already observed this exact process happening to other stars across our galaxy, so we are not speculating here. We are watching the universe's own instruction manual play out in real time, light years away. The good news? 5 billion years is a long time. The universe science facts of today suggest humanity, if it survives that long, will have had countless opportunities to find a new home among the stars. But here is the thing. The sun dying is just the opening act, because once gravity starts winning, it does not stop there. Picture the most perfectly engineered highway system you have ever driven on. Every lane flowing, every on-ramp timed just right, every car maintaining its distance from the next. It feels permanent. It feels locked in, like it could run that way forever. That is exactly how our solar system looks today. 8 planets, dozens of moons, millions of asteroids, all moving in orbits so precise that NASA can calculate the position of Voyager 1, the spacecraft launched back in 1977, to within a few miles. But here is the thing about that perfect highway. It is not actually locked in. It is balanced, and balance, given enough time, always finds a way to break. This is what physicists call orbital mechanics. And the long-term story it tells is a slow, creeping instability that most people never hear about. Every planet in our solar system exerts a gravitational pull on every other planet. These are tiny influences right now, barely noticeable across a human lifetime or even across recorded human history. But over millions and billions of years, those tiny gravitational nudges accumulate. Scientists at the Paris Observatory and researchers working with data from NASA's Jet Propulsion Laboratory in Pasadena, California, have run sophisticated computer simulations of our solar system's future, and the results are genuinely unsettling. There is a real, measurable probability, small but non-zero, that Mercury's orbit could destabilize within the next few billion years. And if Mercury goes, its gravitational ripple could nudge Venus. Venus nudges Earth. Suddenly, that perfectly engineered highway has one car swerving, and the whole system risks a chain reaction. Think of it like a tiny pebble dropped into a still lake. The ripple seems insignificant at first, but if the lake is small enough and the pebble keeps dropping, eventually the whole surface is disturbed. This is one of the most surprising space discovery findings of modern orbital science. Our solar system is not a clockwork machine running forever. It is a dynamical system riding a razor's edge of long-term stability. The universe explained through physics humbles you every single time. And if internal gravitational drift sounds unsettling, wait until you hear about what could come crashing in from the outside. Imagine you are driving across the open plains of Kansas on a clear night. No city lights, just you, the road, and a sky absolutely packed with stars. It feels eternal up there, fixed, safe. Now imagine one of those stars is moving, quietly, steadily, directly toward us. Not a meteor, not an asteroid, an entire star with its own gravitational field, its own planetary system possibly in tow, drifting through the galaxy on a path that brings it uncomfortably close to our solar neighborhood. This is not science fiction. This is a real category of cosmic threat that NASA scientists and astronomers at institutions across the United States take seriously, and it comes in more than one form. First, there are rogue stars. Our galaxy is not a static painting. The Milky Way is a dynamic, churning system of over 200 billion stars, all orbiting the galactic center at different speeds and angles. Occasionally, stellar close approaches happen. They are rare on any human timescale, but on a cosmic timescale, they are essentially inevitable. A star passing within even 1 or 2 light years of our Sun would not need to physically collide with anything to cause catastrophic damage. Its gravitational influence alone could reach into the Oort cloud, that vast, distant shell of icy bodies surrounding our solar system, stretching nearly a quarter of the way to the nearest star, and shake loose enormous numbers of comets, sending them cascading inward toward the planets like a cosmic shotgun blast. NASA's WISE mission actually identified several stars making relatively close passes to our solar system over the coming millions of years, giving us real data on just how real this threat is. But rogue stars are only part of the story. Dark matter is the other player here, and it is one of the most fascinating, unsolved mysteries in all of space science. We cannot see it. We cannot touch it. But researchers at Fermilab in Illinois and astrophysicists across the country have confirmed it makes up roughly 27% of the total content of the universe. Some models suggest that dense filaments or clumps of dark matter drifting through the galaxy could gravitationally perturb our solar system in ways we are only beginning to understand. The universe explained in full always comes back to this humbling truth. Most of what shapes our fate is completely invisible to us. We tend to think of danger as something we can see coming. But the cosmos does not work that way. The threats are quiet, patient, and often arrive from directions we never thought to look. And speaking of threats arriving from unexpected directions, the largest collision in our cosmic future has already been confirmed, and it is coming whether we are ready or not. Here is a space discovery fact that sounds like it belongs in a movie but is completely scientifically confirmed. Our galaxy is going to collide with another galaxy. The collision has already begun, and there is absolutely nothing anyone can do to stop it. The Andromeda galaxy, a sprawling island of over 1 trillion stars, is currently racing toward the Milky Way at roughly 70 miles per second. That sounds fast, and it is, but the distances involved are so vast that on any human timescale, the approach is invisible to the naked eye. NASA's Hubble Space Telescope team, working with researchers across American universities, has measured this approach with extraordinary precision and confirmed what the models have been predicting for decades. In approximately 4.5 billion years, these two galaxies will begin their merger, an event so enormous it does not even have a clean human analogy. But here is the part that surprises almost everyone when they first hear it. This collision will not be like two cars smashing into each other on an interstate. It will not be a wall of stars crashing into another wall of stars. Galaxies are almost entirely empty space. The actual stars within each galaxy are so far apart relative to their size that the probability of any two stars directly colliding during the merger is extraordinarily small. Think of it this way. Imagine taking two large handfuls of sand and throwing them at each other across a football field. The grains of sand are the stars. The air between them is the space. Most of those grains pass right through without ever touching. What will be catastrophically disrupted, however, is gravity itself. The gravitational architecture of our entire galaxy will be torn apart and rebuilt. Stellar orbits that have held steady for billions of years will be thrown into chaos. Our solar system could be flung into an entirely different region of the newly merged galaxy, a region with different radiation levels, different neighboring stars, different cosmic conditions entirely. NASA's Hubble and James Webb Space Telescope observations of other galaxy mergers happening across the universe give us a vivid preview of what this looks like. Dramatic tidal streams of stars, bursts of new star formation, and the graceful, violent reshaping of structures that took billions of years to form. The universe explained at this scale stops feeling abstract and starts feeling deeply, personally real. Our night sky will eventually look nothing like it does today. Andromeda will grow larger and larger on the horizon over millions of years until it dominates everything above us, a second galaxy stretching wall to wall across the darkness. And after all of that, after the sun dies, after the orbits decay, after the galaxies merge, the universe still has three final, breathtaking theories about what waits at the very end of everything. We have watched the sun burn out. We have seen orbits unravel. We have witnessed two galaxies collide in slow-motion grandeur. But now we arrive at the deepest question of all. What happens to everything? Not just our solar system, not just our galaxy. Everything. Every atom, every particle, every last flicker of energy in the entire observable universe. Three theories in modern cosmology attempt to answer that question, and each one is more mind-bending than the last. The first is heat death. This is the theory most physicists currently consider the most likely long-term fate of the universe, and it is quietly, almost peacefully, terrifying. The second law of thermodynamics tells us that energy in any closed system naturally moves toward disorder. Heat flows from hot places to cold places, never the other way around, until everything reaches the same temperature. Applied to the entire universe, this means that over an almost incomprehensibly vast stretch of time, we are talking timescales that make the current age of the universe look like a single heartbeat. Every star will burn out. Every black hole will slowly evaporate through a process predicted by physicist Stephen Hawking, and the universe will settle into a state of perfect, uniform coldness. No heat gradients means no energy flow. No energy flow means no work can be done. No work means no life, no light, no motion. Just an endless, frozen stillness stretching in every direction forever. Think of it like the last ember in that campfire we talked about at the very beginning of this video. It glows, it fades, and then there is just darkness and cold ash. The second theory is the Big Rip. This one is far more violent. It hinges on dark energy, that mysterious repulsive force that NASA's supernova observations in the late 1990s, led by American researchers who went on to win the Nobel Prize, confirmed is actually accelerating the expansion of the universe. If dark energy keeps strengthening over time, the expansion of the universe will not just continue, it will accelerate without limit. Galaxies will be ripped apart, then solar systems, then planets, then atoms themselves, torn apart at the subatomic level as space itself expands faster than the forces holding matter together can resist. The universe does not fade in this scenario. It tears. The third theory is the one that keeps theoretical physicists up at night: vacuum decay. This is where our understanding of quantum field theory leads us to a genuinely unsettling possibility, that the universe we live in is not actually in its lowest energy state. It is sitting in what physicists call a false vacuum, like a ball resting in a small dip on a hillside rather than at the true bottom of the valley. If a quantum fluctuation somewhere in the universe, completely random, completely unpredictable, were to trigger a transition to the true vacuum, a bubble of lower energy space would expand outward at the speed of light, rewriting the laws of physics as it goes. Everything it touches is simply and instantaneously restructured at the most fundamental level. You would not see it coming. Nothing could. It travels at the speed of light, and it rewrites reality itself. Researchers at institutions like the Perimeter Institute and theoretical physics departments across American universities have explored this scenario in serious peer-reviewed science, and the verdict is that we genuinely cannot rule it out. These are not horror stories. They are the universe explained at its most honest, vast, indifferent, and breathtakingly strange. And what makes all of this science so extraordinary is not the endings themselves, but the fact that we are the universe looking at itself, building the tools and the language to understand its own fate. That right there, when that curiosity, that reach, is what Andromeda is all about, and there is so much more of the cosmos left for us to explore together. So here is what we actually learned today. And I want you to sit with this for a moment, because it is genuinely profound. First, endings are written into the laws of physics themselves. The sun is not broken. The universe is not malfunctioning. The fact that our star will one day exhaust its fuel, expand, and transform is not a flaw in the design. It is the design. Stars live, evolve, and die, so that the atoms forged in their cores can go on to build new worlds, new chemistry, and potentially new life somewhere else in the cosmos. Second, our solar system is not the permanent clockwork machine we were taught to picture. It is a dynamical, evolving system balanced on gravitational relationships that shift and drift over deep time. The same NASA science that guides our spacecraft to Jupiter and beyond also tells us, with quiet honesty, that nothing in space lasts forever. Not orbits, not galaxies, not even the universe itself. And third, whether the universe ends in the silent cold of heat death, the violent tearing of the Big Rip, or the instantaneous reset of vacuum decay, the fact that we can even formulate these questions is one of the most extraordinary things about being alive right now in America, in an era where NASA's James Webb Space Telescope is sending back images of the universe's first light, where researchers at universities from MIT to Caltech are modeling the fate of reality itself, and where anyone with curiosity and an internet connection can access the deepest ideas in all of human knowledge. That is the universe mystery that moves me most deeply. Not the endings, but the awareness. Think about that for just 1 second. You are a collection of atoms forged inside ancient stars, sitting on a rock orbiting one of 200 billion stars in one of 2 trillion galaxies, watching a video that explains how all of it eventually ends, and somehow finding that beautiful rather than frightening. That perspective shift, that ability to zoom all the way out and still feel wonder instead of despair, that is what space exploration does for the human spirit. That is what NASA discovery after discovery keeps reminding us. We are not just on this planet. We are part of this universe. And understanding it, even imperfectly, even incompletely, is one of the greatest things we will ever do. If today's Science Explained journey gave you that feeling, even for just a moment, then this video did exactly what it was supposed to do. Go ahead and subscribe to Andromeda right now if you have not already, because every single week we take the biggest, most mind-bending questions in space and physics and break them down with clarity, wonder, and genuine respect for your intelligence. New videos drop every week here on Andromeda, and trust me, what is coming next is going to be worth showing up for. Until then, keep looking up. The universe has a lot more left to show us. Hey, thank you so much for watching this one all the way through. It genuinely means a lot. The fact that you now understand that our solar system is not a permanent clockwork machine, but a dynamically balanced system riding the edge of long-term stability, that is real physics, and you have got it now. And that kind of understanding matters, because as NASA pushes further into deep space and American scientists keep asking the biggest questions about our cosmic future, An informed and curious public is what makes all of that possible. Honestly, exploring these ideas with you is the reason I do this. I'll see you in the next one.